Let's start out tonight with some physics humor. So in this comic strip, we've got a guy that says, "I find you more attractive than usual." And the girl responds, "You do? Is it my new haircut?" And the guy replies, "Actually, I think it's all the weight you've been putting on. Your gravitational pull is pretty severe. Just saying." And that's because anything that has mass has gravity pulling everything around it toward it. You have a force of gravity pulling the things around you towards you. The Earth has a force of gravity. The Earth just happens to be really big because its mass is really big. And the point of this joke, I guess for my lecture, is that your mass, the more mass you have, the more gravity you put on the things around you. And we can calculate the specific force of gravity that any one object puts on another object using this equation. And this is Newton's law of universal gravitation. And it's called universal gravitation because any object with mass has gravity. We can calculate the force of that mass's gravity on another mass using Fg equals big G, which is the universal gravitational constant, times m1, the mass of one object, times m2, the mass of the other object, divided by the distance between their centers squared. So r is the distance between the centers of the masses. Okay, F is a gravitational force, and we'll have units newtons, and it always is an attractive force. As far as we know, there is no repulsive gravitational force. That is, you can't have gravity push two things apart, only pull them together. G is the universal gravitational constant, and it has the value 6.67 times 10 to the negative 11th, and the units meters cubed per kilogram seconds. That's G, and that's what the value of G will always be. M1 and M2 are the masses, measured in kilograms, and it doesn't actually matter the order you put them in, so multiplication is commutative. You can change the places of the m's, and so it doesn't matter which one you call M1 and which one you call M2. R is the distance between the centers of mass, and it is measured in meters. And notice that the force of gravity on either mass, so no matter which one you call mass 1 and mass 2, you'd still get the same force. So the force of gravity is the same for both of the masses involved. So if you're thinking about you and a cup sitting near you, you put as much gravity on the cup as the cup puts on you. And you put as much gravity on the Earth as the Earth puts on you. At least as much force of gravity, I should say. You put as much force of gravity on the cup as the cup puts on you. You put as much force of gravity as the Earth puts on you. And that is a requirement of one of Newton's laws we've already studied, Newton's third law. Newton's third law says that if one object puts a force on another, the second object puts the same force in the opposite direction on the other object. So the Earth pulls you toward it, you pull the Earth toward you. You pull the cup sitting next to you towards you, it pulls you toward it. Now, there's all kinds of friction involved, and the Earth's force of gravity is much bigger, so we only notice the one from the Earth. Often when using that equation, it's more useful to do the math without a calculator because you can actually do these calculations in your head faster than entering them in the calculator. And I'm going to show you an example of that by finding the force of attraction between the Earth and the Sun. Anytime you're finding the force of attraction between two massive objects, at least massive big objects, you're going to use gravity. When we get to really small objects, we might use some other forces like electrical forces, what's called the strong and weak force. But here, objects out in, say, outer space, we're going to use Newton's law of universal gravitation, which is big G times one of the masses times the other mass, should have been mass 1, divided by the distance between their centers of mass squared. So G, showed you on the last slide, is 6.67 times 10 to the negative 11th meters cubed per kilogram seconds. So ignore that, kilograms. Okay, and I quickly looked up the information we'd need for the rest of this problem. The mass of the Earth is about 6.6 times 10 to the 24th kilograms. The mass of the Sun is about 2 times 10 to the 30th kilograms. The distance between the center of the Earth and the center of the Sun is 1.5 times 10 to the 11th meters. And now we can use those values in the equation. Fg equals 6.67 times 10 to the negative 11th meters cubed per kilogram seconds times 6 times 10 to the 24th kilograms 2 times 10 to the 30th kilograms divided by 1.5 times 10 to the 11th meters squared. Okay, so I can do a lot of this without the calculator. When I'm dealing with exponents, exponents add when multiplied, and then the numbers in front, so the 6 and the 2, they would just get multiplied. So I can multiply 6 and 2, and then add their exponents. And so that part reduces to Fg equals 6.67 times 10 to the negative 11th meters cubed per kilogram seconds times 12 times 10 to the 59th kilograms squared over, the same rules apply for squaring, so I square the 1.5, and 1.5 times 1.5 will be less than 3, because 1.5 times 2 would be 3, but definitely bigger than 2, so I'm going to guess that 1.5 times 1.5, or better than guessing, 1.5 times 1.5, and I get 5, carry the 2, 7, 5, 1, 2.25. Okay, so 2.25, and the square will double the other part, the exponent, 10 to the 22nd meters squared. When I multiply a negative exponent and a positive exponent, they will subtract. And 6.67 is going to be a little difficult for me, so I'm just going to say it's about 7. We can estimate here. And I'll get on the top 84 times 10 to the negative 48, or sorry, positive 10 to the 48th. I really messed that up. 10 to the 48th, so 59 plus negative 11, divided by 2.25 times 10 to the 22nd. Okay, now I'll divide the bases and subtract the exponents. So 84 divided by 2.25. Sorry, I had to grab some scratch paper. I got about 37, and then since the exponents are divided, we'll subtract. So 48 minus 22 leaves me with 26 newtons. 37 times 10 to the 26 newtons. Now I want to check me on that. That was a lot to do without a calculator. But you can do this with estimating, and you've learned a little bit about how to multiply exponents in scientific notation. So the exponents add together when multiplied and subtract when divided. Tomorrow you're going to use this information to solve lots of problems. Some of them say don't use a calculator, some of them do, and you should do that as they say. That's all. Have a good night.